If I told you that the entire North American power grid and, the multi-trillion-dollar economy it basically supports
Yeah.
could be completely brought to its knees by an event that takes less than 2 minutes, you'd probably assume I was talking about, like, a coordinated cyber attack.
Right, or some kind of devastating kinetic weapon.
Exactly. But I'm not. I am talking about a sunny day in the 1850s, or, honestly, even more subtly, just a few degrees of ambient summer heat.
Yeah, which is kind of terrifying when you really think about it.
It is. Like, think about this for a second. Have you ever been sitting in a quiet room, maybe you're working on a heavy spreadsheet or rendering a video, and you suddenly notice your laptop fan just spinning up?
Oh, yeah, it sounds like a tiny jet engine taking off right on your desk.
Right. And for you, it's just this minor, acoustic annoyance. But I want you to hold on to the physical reality of that sound, because that fan is a desperate mechanical gasp to dissipate heat before the delicate electronic brain of your machine literally cooks itself.
It's a survival mechanism.
It really is.
Yeah.
Now, take that exact same vulnerability, that desperate need to shed thermal energy, and scale it up to the sprawling, continent-wide, high-voltage power grid you rely on every second of every day.
Which is massive.
Massive. And then scale it all the way down to a completely sealed, military-grade metal box sitting in the middle of a blazing desert trying to run critical artificial intelligence, but without a single fan or vent.
It forces a profound and, frankly, a really uncomfortable shift in perspective. I mean, you are forced to stop viewing heat merely as a weather condition or, a minor inconvenience.
Right.
And you have to start recognizing it as the fundamental, inescapable governor of modern civilization.
Which is exactly why we are opening this brand new deep dive today. Our mission is a comprehensive investigation into something called the Osgood-Rupert Node Technical Archive.
It's quite a stack of documents.
Oh, it's an incredibly dense, fascinating stack of sources today. We've got technical memorandums on solid-state physics, historical benchmark reports dating back to the 19th century, and some deeply unsettling philosophical analyses on the thermal architecture of our society.
Yeah, the scope of it is really something.
It really is. We are exploring the intersection of systemic infrastructure fragility and the highly experimental engineering required to protect the electronic brains of our future from, well, the most extreme elements the universe can throw at them.
By the end of this deep dive, the way you look at a summer heat wave, or a power line, or even a starry night sky, it's going to fundamentally change.
Okay, let's unpack this. Because
Yeah.
starting with the macro-level philosophical framework is basically essential to understanding the actual technical crisis here.
Absolutely. What makes the Osgood-Rupert archive so uniquely compelling is that it refuses to separate the engineering from the psychology.
Right. Before it even presents a single blueprint or schematic, it forces us to confront our own cognitive blind spots regarding the machines we built. The archive introduces this concept it calls the human OS, like our human operating system.
Yeah, and it's a great term.
When I was reading through this initial thesis, it just struck me how perfectly it diagnoses a cognitive bias we all share. The thesis argues that our human OS has this terrible psychological habit of confusing structural mass and historical permanence with actual resilience.
We process visual weight as invulnerability. I mean, think about it. When you stand at the base of a massive high-voltage transmission tower, or you look at a sprawling concrete hydroelectric dam, your brain registers a monolith.
Totally.
You see thousands of tons of forged steel, thick aluminum cables, poured concrete. The human OS naturally equates that sheer physical mass with an absolute permanence.
We just assume the power grid is this indestructible, immovable vault. Because, well, it feels heavy and it has functioned historically throughout our own relatively short lifetimes.
The lights have always come on when we flick the switch, so our operating system assumes the lights will always come on.
Right, but the archive totally shatters that illusion with a metaphor that is both brilliant and deeply unsettling. They call it the banana stand thesis.
Which is such a great reference.
It's so good. It's a nod to the show Arrested Development, where the corrupt family hides all their embezzled cash inside the walls of a frozen banana stand on a boardwalk. And the patriarch constantly insists that the stand is a vault. It's safe. There is always money in the banana stand.
But the critical, fatal flaw of that strategy, which the archive isolates and applies to our macro grid, is that it is a frozen banana stand.
Frozen being the key word.
Exactly. The vault is entirely dependent on an active compressor. It requires a continuous, uninterrupted flow of electricity just to keep that highly specific artificial environment stable.
And the moment the power to the compressor drops.
The structural integrity of the vault literally melts away.
That is the terrifying realization I had when reading the projections for the Southeast United States grid. Our entire society is treating a fragile, actively cooled, heat-sensitive system as an indestructible vault.
Yeah, we are essentially banking the continuity of modern civilization on a giant kitchen appliance never losing power.
It's wild. And the archive points directly to the summer 2026 projections, heavily stressing the regional power networks, specifically the TVA, the Tennessee Valley Authority.
The TVA projections highlight a reality where hotter than normal ambient temperatures become the baseline, rather than just an anomaly. And the danger isn't merely a linear increase in power demand.
Right. It's not just everyone turning on their AC.
Exactly. When the macrogrid hits extreme heat, you don't just see a spike in consumption. You trigger a cascading effect of systemic thermodynamic degradation.
It's a trap closing from multiple sides at once. Like the moment the heat wave hits, millions of residential and commercial air conditioning units kick on simultaneously, drawing massive, sustained current.
Which stresses the lines immensely.
Yeah. But it was the second factor in the cascade that really made me realize how vulnerable the generation side is. The power plants themselves are physically throttled by the very heat wave driving the demand.
Because thermodynamics does not care about economic reliance or human comfort?
No, it really doesn't.
Whether a power plant is nuclear, coal, or natural gas, the fundamental mechanism of generation relies on a temperature differential. You are boiling water to spin a turbine, and then you must aggressively cool that steam back into liquid water to maintain the cycle's efficiency.
Right, and they rely on massive local heat sinks for that, typically drawing millions of gallons from local rivers or lakes.
Exactly. So if the ambient temperature of that river water is too high, the thermodynamic delta shrinks. The plant physically cannot cool itself effectively.
Wow.
And the operators have absolutely no choice but to throttle down the power output to prevent the core generation equipment from damaging itself.
Wait, so you're saying our entire modern society is basically banking on a kitchen appliance not losing power during a heat wave? Like, the physics dictate that right at the precise millisecond, our society is demanding the absolute maximum amount of electricity to stay cool. The massive concrete monoliths generating that electricity are fundamentally incapable of producing it.
Yes, because their cooling water is too warm, you have demand skyrocketing and supply mathematically forced to drop.
That is insane.
And that leads directly to the third and probably most insidious factor of the heat cascade, the destruction of transformer integrity.
The extra high voltage transformers.
Right. These massive multi-ton steel boxes that step power up for long-distance transmission and then step it down for your local substation. They are essentially giant pressure cookers filled with mineral oil.
And that oil is not just a lubricant, right?
Yeah.
It acts as a critical liquid coolant and an electrical insulator.
Precisely, because transforming that much voltage generates an immense amount of internal heat.
So now you combine that massive internal thermal load with an extreme external ambient heat wave.
The oil expands, the pressure inside the casing builds, and the physical seals on the transformer begin to degrade.
Oh, man.
The oil can leak out, the internal insulation breaks down, the transformer can catastrophically fail. It literally cooks its own internal components.
The vault melts, the compressor fails, the frozen banana stand thaws, and the structural illusion of the monolith just collapses.
Exactly.
We were operating on these deeply fragile 20th century engineering baselines, assuming the climate of the 1970s will hold steady, while we slam headfirst into 21st century thermal extremes. We might as well be 19th century telegraph operators just blindly hoping the wire doesn't snap.
Which raises a really important question. If the macrogrid is demonstrably this vulnerable to ambient heat and cascading failure, how do you ensure the continuity of critical infrastructure?
Right. You have to pivot.
You do. The logical engineering pivot and the primary focus of the Osgood-Rupert Node archive is decentralization.
Yeah.
You move away from the massive fragile web. You build micronodes, edge computing environments.
So you take your critical artificial intelligence, your emergency communications hubs, logistical processing cores, and you seal them inside highly ruggedized, military-grade enclosures.
Yes. You try to completely isolate them from the macrogrid's failure and the external weather.
See, here's where it gets really interesting.
Yeah.
Because when I was reading the documentation, I fully expected the solution to just be, build a really tough box.
That's what most people think.
Yeah. But the archive reveals that when you try to escape the macrogrid's fragility by building these decentralized, sealed micronodes, you don't actually solve the thermal problem, you just compress it.
You run into a brand new, terrifying micro-level thermal nightmare.
Exactly. And The documentation refers to the environmental baseline of these ruggedized boxes as Hoth conditions.
Which is a brilliant piece of engineering shorthand, honestly, but one that is often vastly misunderstood due to pop culture.
Right, from Star Wars.
Yeah. When an engineer defines a test environment as Hoth, they aren't merely talking about absolute zero or sustained freezing cold. What's fascinating here is that extreme, stable cold is rarely the primary enemy of solid-state electronics.
Here's where it gets really interesting. I always thought Hoth meant freezing to death, but you're saying it's the swing between freezing and boiling that actually breaks the bones of the circuit board.
The true hardware nightmare, the condition that aggressively destroys circuit boards in the field, is extreme thermal cycling. The swing.
It isn't the freeze that kills you. It's the violent transition from freezing cold to boiling hot and then rapidly back again.
Exactly. The archive details the failure mechanisms of these edge nodes inside sealed enclosures, breaking it down into an incredibly detailed three-headed monster.
It is a perfect storm of mechanical, chemical, and thermodynamic failure. Let's look at the first head of that monster, thermal cycling fatigue.
Right. This operates at the microscopic architecture of the internal components. An edge AI node might sit completely idle for hours in a freezing desert night.
So it's literally ice cold.
Yes. But the moment it receives a complex data set to process, the core compute unit spikes to a full 100% processing load. It generates a localized wave of intense heat almost instantaneously.
And basic physics dictates that materials expand when they heat up, right? So the internal landscape of that computer is suddenly shifting. But it's not expanding uniformly.
No, not at all.
I remember looking at the material breakdown in the archive. You have the pure silicon of the processing chip, the fiberglass composite of the actual circuit board, and the metal alloy solder joints that are physically gluing and electrically connecting them all together.
Every single one of those materials possesses a radically different coefficient of thermal expansion.
Meaning they grow at different speeds.
Exactly. The metal solder expands at one rate, the fiberglass board swells at another, and the silicon chip expands at a third. As the high compute heat wave washes over the board, those microscopic solder joints are physically stretched and warped.
And then the compute task finishes.
The processor idles, the heat dissipates, and the materials rapidly contract again at completely different rates.
It's literally like microscopic tectonic plates grinding against each other.
Precisely. You are physically bending and torquing the microscopic solder joints back and forth with every single spike in computational demand.
Ouch.
Over time, this cyclic expansion and contraction introduces microstresses. Hairline fractures begin to propagate through the solder. It's simple metal fatigue.
Like bending a paperclip back and forth until it snaps.
That's exactly it. Eventually, the connection snaps, the electrical pathway is severed, and the node quietly dies.
So the thermal swing literally fractures the bones of the circuit board. But the mechanical fracturing is really just the physical degradation. When you look at the chemical side of the environment, specifically the power delivery during a cold start, the problem gets even more insidious.
The second head of the monster.
Right. Electrolyte degradation.
This failure mode is entirely chemical and electrical. Consider the capacitors on that circuit board. Capacitors are essentially localized energy reservoirs, right?
And to smooth out the power supply.
Right. Their function is absorbing spikes and providing quick, instantaneous bursts of energy to the processor during heavy loads. Well, many high-capacity components rely on a liquid electrolyte to function.
And when that ruggedized box has been sitting in sub-zero Hoth temperatures overnight, that liquid electrolyte doesn't necessarily freeze solid, but it fundamentally changes state.
It does. The archive notes a massive increase in viscosity. The electrical blood of the machine thickens.
Wow, what a visual.
As that viscosity increases, the internal resistance, the impedance of the capacitor skyrockets. It can no longer rapidly absorb or discharge energy.
So when the processor suddenly demands a clean, steady flow of direct current to execute a critical AI calculation, the thickened capacitor basically struggles.
Instead of a smooth, flat line of power, it delivers a fluctuating, erratic wave. Engineers refer to this as a voltage ripple.
And in the highly sensitive binary logic of a modern processor, a voltage ripple isn't just, an inefficiency. It's a catastrophic event.
Absolutely.
A processor relies on precise voltage thresholds to differentiate between a 1 and a 0. If the power supply ripples at the exact wrong microsecond, a 0 registers as a 1.
The logic cascades into chaos. The machine essentially loses its mind because it cannot trust its own internal state.
So the bones fracture from the expansion, the logic corrupts from the thickened electrolytes, and finally we arrive at the third head of the monster, which just traps the system entirely.
Thermal saturation.
Yes. The archive explicitly links this back to our earlier macro metaphor. This is the banana stand effect applied to a tightly sealed, closed-loop microenvironment.
By definition, a ruggedized military or field case must be completely sealed against the elements. It has to survive being dropped in a river, buried in a sandstorm, rattled in the back of a tactical vehicle.
You cannot have any open vents.
No vents. You cannot have spinning intake fans dragging dusty, corrosive air over the delicate electronics.
But the necessity of that isolation creates a thermodynamic prison. When the heavy compute cycle begins, the massive amount of heat generated by the processor has absolutely no escape vector.
None. It builds rapidly within the sealed chassis.
And the internal air temperature climbs until it reaches total saturation.
Right.
Like the specific point where the volume of air inside the box simply cannot absorb another joule of thermal energy from the silicon.
And that triggers a desperate survival mechanism within the software itself. The processor's internal thermal sensors realize the environment is saturated. To prevent catastrophic physical melting of the silicon gates, the operating system aggressively intervenes.
It forcefully slows its own thinking down to a crawl to choke off the heat generation.
It forcefully throttles the CPU clock speeds. The node effectively lobotomizes itself.
Right at the critical moment of peak demand, like when the AI needs to process a vital logistical route or a survival protocol, the machine just goes to sleep to save its own life.
The closed-loop banana stand fails from the inside out because the thermal debt cannot be paid.
So what does this all mean for the engineering reality? We have diagnosed a terrifying multi-layered vulnerability inside a sealed box. My immediate, uneducated instinct when reading about thermal saturation was to look to the high-end PC gaming world.
Oh, like liquid cooling.
Yeah. Why not just pipe a liquid cooling loop through the sealed box? Circulate chilled water or a specialized coolant over the processor and run it to an external radiator. But the Osgood-Rupert Memorandum explicitly bans that.
Yes, it does.
No liquid loops, no toxic refrigerants, and absolutely zero active mechanical parts.
It comes down to the fundamental difference between a controlled laboratory environment and a hostile field deployment. If you integrate a pressurized liquid cooling loop inside a ruggedized chassis, and that chassis is subjected to the intense vibrational shock of a helicopter drop or an artillery blast, an internal fitting will inevitably fracture.
You trade a thermal vulnerability for a devastating mechanical vulnerability. A cracked liquid line inside a sealed electronics case isn't a degraded system. It is an instant catastrophic short circuit.
The very mechanism designed to protect the system destroys it.
So this absolute constraint forces a radical departure in design philosophy, which brings us to the core technical solution detailed in the archive.
The technical memorandum? Passive thermal buffering?
Engineers had to develop the Hoth buffer architecture, a system that cools a high-performance computer without a single moving part, without a drop of liquid, and without opening a single vent to the outside world.
You have to fundamentally change your philosophical relationship with heat. You have to stop treating thermal output as a toxic byproduct that must be actively blown away and start treating it as a massive energy surge that must be absorbed, stored, and managed.
And the first pillar of this solid-state Hoth buffer architecture relies on something called PCM's phase change materials.
The physics of a phase change are a masterclass in exploiting natural laws for engineering game. Consider the simple thermodynamics of a glass of ice water. As long as there is physical ice remaining in that glass, the temperature of the water will remain locked exactly at the freezing point. It will not, and physically cannot, get warmer until every single ice crystal has absorbed enough energy to transition into a liquid state.
Because the process of changing the state of matter from solid to liquid requires a massive continuous input of energy just to break the molecular bonds.
Exactly. That energy is called latent heat.
The substance absorbs the heat, but its temperature doesn't rise while it's melting. It's the ultimate thermal shock absorber.
Engineers leverage this exact principle using highly specialized non-toxic materials, often advanced paraffin-based waxes or salt hydrates.
Right.
These PCMs are engineered at the molecular level to melt at highly specific operational temperatures, let's say exactly 45 degrees Celsius. They seal this wax into dense, solid grids and line the entire internal cavity of the ruggedized chassis with them.
So instead of fighting a sudden heat spike with a fragile, loud, spinning fan, you are essentially giving the computer a high-tech paraffin wax bath that just eats the heat. That's one way to look at it, yes.
It's like thermal judo. When the AI node spikes to a 100% compute load, it unleashes a massive wave of heat. But instead of the internal air temperature violently rising and triggering thermal saturation, that wave of heat hits the PCM packets.
And the energy is entirely consumed by the physical process of melting the solid wax into a liquid. The ambient temperature inside the sealed box stays perfectly, unnervingly flat. It buffers the surge.
It acts as a localized heat battery, it charges up by melting, and the brilliance of the system is entirely passive.
Yes, when the compute load drops and the processor idles, the ambient temperature of the external environment begins to pull that stored heat out of the case.
The liquid wax slowly dissipates its stored thermal energy, re-solidifying back into a rigid state, perfectly resetting itself for the next spike.
It's an elegant intrinsic cycle.
But as I read further, I realized the wax has a finite capacity. I mean, if the AI node has to run a heavy compute load for hours, the wax will eventually fully melt, the latent heat absorption will stop, and the temperature will spike. Right, you can only absorb so much.
So you need a way to actively move the baseline heat out of the core to give the wax time to recover and resolidify. And that requires the second pillar of the architecture.
Thermoelectric modules. Specifically, Peltier modules.
The memo describes these as thin, solid-state ceramic plates. But how do you move heat through a solid piece of ceramic without a pump?
The Peltier effect is a deeply fascinating quirk of quantum mechanics and solid-state physics. A Peltier module contains no moving parts, no gases, and no liquids.
Okay.
It is constructed of dozens of alternating P-type and N-type semiconductor pillars sandwiched tightly between two highly conductive ceramic plates.
So it basically leverages the movement of electrons.
Exactly. When you apply a direct current DC power across this semiconductor array, you are physically forcing electrons to move from a lower energy state to a higher energy state.
And to achieve that state change, the electrons must absorb energy for their immediate surroundings.
They literally absorb ambient thermal energy at one side of the ceramic plate, physically carry that heat as they move through the semiconductor lattice, and then release that heat as they drop back to a lower energy state on the opposite ceramic plate.
It is literally an electron bucket brigade. You are pumping heat using nothing but the flow of electricity. One side of the ceramic plate drops to freezing temperatures, while the other side becomes scalding hot.
Yes. You place the freezing side directly against the processor core, and you place the scalding side against the heavy internal aluminum frame of the ruggedized case.
You are forcibly extracting the heat from the delicate silicon, entirely bypassing the stagnant air inside the sealed box, and injecting that thermal energy directly into the massive metal walls of the chassis.
But to ensure that the solid-state pump operates at maximum efficiency, you must eliminate any microscopic insulating gaps between the components.
Which brings us to the third and final pillar of the architecture, graphene heat spreading.
Graphene is remarkable here.
It always sounds like science fiction until you see the numbers. It is a single, isolated layer of carbon atoms, perfectly arranged in a two-dimensional honeycomb lattice.
Like this.
The memo details using thick, highly compressed graphene thermal pads to bridge the physical gap between the compute unit like, say, a decentralized Raspberry Pi 5 array and the aluminum structural frame. Why is graphene the linchpin here?
Because the thermal conductivity of graphene vastly outstrips almost any other known material. Heat moves through materials via vibrations called phonons.
Oh.
The incredibly rigid, perfectly ordered carbon lattice of graphene allows these phonons to travel with almost zero resistance. It acts as an absolute superhighway for thermal transport.
Wow.
By using graphene pads, you completely eradicate any microscopic insulating pockets of air between the Peltier module and the case. You create a mathematically perfect thermal bridge.
When you synthesize all three pillars, the elegance of the engineering is staggering. You have the Peltier module actively pumping the heat away from the silicon brain. You have the graphene pad acting as an incredibly fast superhighway, rushing that heat directly into the thick metal walls.
And you have the paraffin wax batteries lining the interior, quietly eating any sudden violent spikes in temperature that the pump can't instantly handle.
You have turned the entire heavy military case itself into one giant solid-state passive radiator. It literally bleeds the heat out into the desert night air without opening a single mechanical vent.
And that is the true philosophy of the Hoth buffer. It achieves complete thermal stability for the local AI's operating temperature without relying on a single mechanical point of failure.
It entirely eliminates the violent thermal cycling that fractures solder joints.
Right, and it prevents the internal ambient air from reaching saturation. It accomplishes this intrinsically, relying purely on the fundamental physics of phase changes, semiconductor electron flow, and carbon lattice conductivity.
We have solved the micro problem. We have successfully engineered a way to protect the decentralized edge nodes from their own heat in the middle of a hostile void. But,
Did a big but.
yeah, here is where the Osgood-Rupert archive takes a massive, terrifying pivot. The documentation essentially says, well, congratulations, you built a highly survivable solid-state box. But what happens when the universe decides to test the macro grid with an event that makes a summer heat wave in the southeast look like a rounding error?
The ultimate test of our systemic infrastructure fragility isn't the ambient temperature in 2026. It is the existential threat of space weather.
Which brings us to the critical transition in the archive's historical benchmark files. We have to pivot away from local thermodynamics and look at the Carrington event of 1859.
If the banana stand of our modern electrical grid is dangerously fragile to a warm summer day, a Carrington-level event is a cosmic wrecking ball swinging with incalculable kinetic energy straight for the vault.
The narrative the archive provides for 1859 is incredible.
Yeah.
We really need to set the scene to understand the sheer scale of the energy involved. We do. It's September 1st, 1859. We are in Surrey, England. A dedicated amateur astronomer named Richard Carrington is up in his private observatory. He's engaged in his daily routine, projecting an image of the sun through his telescope onto a screen to safely sketch sunspots. It's a completely normal morning.
Right.
And then he witnesses something that no human being had ever definitively recorded before. He sees two patches of intensely bright, sudden white light erupting directly out of the massive sunspot group he is drawing.
The flash of brilliant light lasted for maybe 5 minutes before fading.
What Richard Carrington was witnessing in real time was the first recorded observation of a massive solar flare.
But the brilliant flash of white light, traveling at the speed of light and reaching his telescope 8 minutes after it erupted, was merely the visual warning siren.
What Carrington could not see through his lens, following violently behind that flash of light, was the coronal mass ejection, a CME.
A CME isn't just light. It is a physical cloud of highly magnetized solar plasma. It is a massive chunk of the sun's outer atmosphere physically torn away and hurled across the solar system directly at Earth.
And the archive heavily emphasizes the anomalous speed of this specific ejection. Normally, a CME takes several days to slowly cross the 150 million kilometers between the sun and our planet.
But the plasma cloud from Carrington's flare crossed that immense void in just 17.6 hours.
The velocity of that transit indicates a level of kinetic energy that just defies easy comprehension.
When that massive, incredibly fast-moving cloud of magnetized plasma violently slammed into Earth's protective magnetosphere, the impact physically compressed our planet's magnetic field.
It fractured our magnetic shielding, right?
Yeah.
Allowing highly charged solar plasma to pour directly into our upper atmosphere.
Yes. It triggered the most severe geomagnetic storm ever recorded in human history.
The visual effects reported around the globe sound like descriptions from a surreal science fiction novel. The auroras, the northern and southern lights, which are usually confined to the extreme polar regions, were so supercharged with solar energy that they expanded massively toward the equator.
There are documented reports of auroras being visible as far south as Panama and Hawaii.
The archive includes a famous account of gold miners in the Rocky Mountains who woke up at 1 a.m., saw the sky glowing so intensely bright that they assumed it was morning, and actually began brewing coffee and making breakfast.
People in the northeast United States reported sitting on their porches at midnight, easily reading the fine print of their newspapers entirely by the shifting light of the night sky.
But the global auroral display was just a majestic visual spectacle. It was entirely harmless to biological life.
The true danger, and the sole reason the Osgood-Rupert archive focuses so heavily on this event, was what the storm was doing at the ground level, hidden within the newly laid electrical infrastructure of the era.
The telegraph phenomena.
Yeah.
In 1859, the absolute pinnacle of human electrical engineering was the global telegraph network. It was the Victorian Internet. And suddenly, on September 1st and 2nd, telegraph operators around the world started experiencing a terrifying cascade of anomalies.
Electrical sparks were violently leaping from their transmission keys. The chemical paper tape used to record incoming messages was spontaneously catching on fire.
Operators were receiving severe physical shocks through their equipment. But the detail that truly blew my mind is what happened on the night of September 2nd between two specific operators in Boston and Portland, Maine.
The archive cites the compilation of records regarding those specific operators. The ambient electromagnetic currents flowing through the Earth, driven by the shifting solar storm above, were so incredibly powerful and so remarkably steady that the operators in Boston and Portland made a radical decision.
They physically unplugged the primary chemical batteries from their telegraph lines. They completely disconnected their man-made power source.
And for over 2 hours, they continued to seamlessly send and receive messages across miles of wire, powering their heavy equipment using absolutely nothing but the immense auroral current induced by the solar storm.
See, when I read that, my first thought was almost optimistic. Like, if it powered telegraphs back then, what does it do to our grid now? Does it just give us free electricity? Why is the archive presenting this as an apocalyptic threat rather than an energy windfall?
It is a catastrophic threat because of a fundamental, irreconcilable difference in how Victorian telegraphs operated versus how a modern, high-voltage power grid operates.
Okay, lay out.
The telegraph networks of 1859 ran on direct current DC power. Direct current is a flat, steady, continuous flow of voltage in one single direction. A modern, extra-high voltage power grid operates entirely on alternating current AC power.
Right. AC power constantly oscillates, rapidly reversing its direction of flow, like 60 times a second in the North American grid.
Exactly. So how does the massive auroral current from a CME interact with an oscillating AC grid? To understand the destruction, we must look at the mechanics of geomagnetically induced currents, or GICs.
GICs.
When that massive cloud of solar plasma compresses and disturbs Earth's magnetic field, it creates deep, slowly varying magnetic fluctuations that penetrate deep into the Earth's crust.
And Faraday's law of induction, a bedrock principle of electromagnetism, dictates that any changing magnetic field will inevitably induce an electrical current within any long electrically conducting structure.
Like the hundreds of thousands of miles of high-voltage transmission lines strung across the North American continent.
The lines we assume are delivering our power suddenly act as continent-spanning antennas, absorbing the energy of the solar storm directly from the shifting magnetic field of the Earth itself.
Exactly. And the crucial, devastating detail is that the current induced in those massive transmission lines by the solar storm is a quasi-direct current. It is a slow, massive, flat flow of DC energy.
And this massive GC wave travels unchecked down the transmission lines until it inevitably hits the extra-high voltage transformers located at the regional substations.
Now remember, those massive transformers are engineered with extreme precision strictly for AC current. They rely on the rapid 60 Hz oscillation of the AC wave to smoothly induce and release magnetic flux within their massive iron cores, transferring power without ever fully saturating the metal.
So what physically happens inside that multi-ton steel box when you take a flat, non-oscillating wall of DC current from a solar storm and slam it into an iron core designed exclusively for rapid AC oscillation?
The immense DC current violently shifts the entire magnetic baseline of the transformer's core. It pushes the iron core into a highly destructive state known as half-cycle saturation.
Wow.
Because the core is saturated by the DC wave, it can no longer smoothly process the AC power flowing from the grid. Instead of acting as an efficient step-down transformer, the massive steel box suddenly starts acting like an incredibly inefficient continent-sized space heater.
The thermodynamic nightmare returns.
It generates extreme, uncontrolled internal heat that vastly exceeds the cooling capacity of the mineral oil we discussed earlier.
And furthermore, the saturation produces severe electrical harmonic distortions, like dirty, chaotic power that ripples violently back out through the surrounding grid, causing safety relays to trip and other systems to misfire.
Inside the transformer, the internal insulation literally boils away, the heavy copper windings physically melt, and the multi-million-dollar transformer structurally destroys itself from the inside out in a matter of minutes.
And this brings us to the terrifying modern context that the Osgood-Rupert archive lays out, the cost of inaction.
The modern vulnerability is staggering.
Right, because the 1869 Carrington event was a profound cosmic warning. But in 1859, the absolute worst-case scenario was some burned paper tape and a few shocked telegraph operators. Today, if a Carrington-level event strikes the Earth, it is a wrecking ball hitting a frozen banana stand that stretches across an entire continent.
And the archive proves this isn't just theoretical modeling. We have seen the precursors.
We do not have to blindly guess what a geomagnetically induced current will do to a modern AC power grid. We have observed the collapse in real time.
In March of 1989, a severe solar storm, one that was significantly weaker than the Carrington event, struck the Earth.
The resulting GICs surged directly into the Hydro-Quebec power grid in Canada.
In under 2 minutes, the extreme harmonic distortion caused the protective relays to trip, the entire system structurally collapsed, and 6 million people were instantly plunged into a blackout that lasted for 9 hours.
2 minutes. That is all it took for space weather to take down an entire regional grid. The archive also mentions the Halloween storms of 2003, which physically destroyed extra-high-voltage transformers in South Africa and triggered rolling blackouts in Sweden.
But the detail in the archive that absolutely stopped my heart, the one that makes you realize how thin the margin of survival is, was the near miss of July 2012.
Yes. In July 2012, the sun erupted with a coronal mass ejection of true, unquestionable Carrington-class intensity.
The Stereo, a space observatory, recorded the eruption and its massive velocity. The plasma cloud crossed the exact orbital path of the Earth, but it missed our physical planet by approximately 9 days of orbital motion.
When I read that, the reality of it just floored me. 9 days of orbital motion. We always talk about space weather as if it's a sniper aiming at us.
Yeah.
But a CME is a massive cosmic shotgun blast.
We simply happened to walk out of the line of fire slightly before the trigger was pulled. If that eruption had occurred just over a week earlier, we would have taken a direct catastrophic hit.
That extraordinarily close call prompted a severe, panicked recalculation of our global exposure. The archive highlights a comprehensive risk model published in 2013 by the insurance market Lloyd's of London, in collaboration with atmospheric and environmental research.
They sought to calculate the pure economic and logistical impact if a Carrington-level storm, identical to 1859, struck the present-day North American macro grid.
The numbers in that report are staggering, and they completely reframe the concept of a natural disaster. They estimate the upper bound economic damage to the United States alone at $2.6 trillion.
They project that between 20 and 40 million Americans would instantly lose power.
And the truly terrifying part is the duration. We are not talking about a power outage that lasts for 9 hours, like the Quebec incident. The Lloyd's model estimates blackout durations ranging from 16 days at the absolute optimistic low end, stretching to 1 to 2 full years at the high end.
If we connect this severe duration to the bigger picture of systemic fragility, you have to critically ask, why would an electrical outage in a developed nation possibly last for 2 entire years?
Right. It seems impossible.
The answer lies not in the wires, but in the brutal reality of the global supply chain. If a summer heat wave takes down a single transformer, utility crews bypass it and eventually replace it from local stock.
But if a Carrington event induces GICs that simultaneously melt the internal cores of hundreds of extra high-voltage transformers across the continent, you are no longer managing a blackout. You are managing a civilization-altering logistical crisis.
Because you can't just run to a hardware store to buy an extra high-voltage transformer.
Exactly. These specific transformers are colossal pieces of bespoke engineering. They weigh hundreds of tons. They are custom-built to specific regional voltages.
The manufacturing lead times for a single new unit run from 5 to 12 months from domestic suppliers and 6 to 16 months if ordered internationally.
You cannot easily stockpile them due to their massive cost and size, and transporting a 500-ton piece of equipment across a country where the rail and highway logistical networks are paralyzed by a lack of power is nearly impossible.
If the transformers melt, you simply have to wait in the dark until new ones are forged.
Wait, let me make sure I'm synthesizing this correctly. So what does this all mean? We are facing a $2.6 trillion potential economic hit, with entire geographic sectors of the country going totally dark for up to 2 years, resulting in unimaginable societal collapse. Versus, what would it actually take to fix this?
The archive mentions a specific physical mitigation strategy. It details installing neutral current blocking capacitors on the 1,000 most vulnerable extra high voltage transformers in the U.S. grid.
As I understand it, these are relatively simple devices that literally block the flat DC current of the solar storm from entering the transformer's ground neutral while perfectly allowing the oscillating AC current to flow normally.
Yes, and the estimated cost to harden those 1,000 critical points, roughly $100 million.
Wait, a $2.6 trillion potential economic hit versus only $100 million needed for hardening? Why aren't we doing this? Is it the human OS striking again, just assuming the volt is safe?
That is the exact psychological trap the Osgood-Rupert archive is warning against in its conclusion. As the document starkly states, a highly electrified modern society that has never once operated continuously through a Carrington-level event carries an unprecedented, untested exposure.
It is a massive assumption of permanence based on a severely limited dataset.
We have culturally normalized the risk simply because the statistical midpoint estimate for a Carrington return period is roughly 150 years. We comfort ourselves by calling it a once-in-a-century event.
But peer-reviewed probability, analyzing ice cores and historical solar data, places the statistical chance of a Carrington-class impact in the next decade at roughly 1 to 10%. That is not a myth. That is a statistical certainty operating over a long enough timeline. It's like we are standing on the beach watching the ocean tide suddenly recede really, really fast, and instead of recognizing the tsunami warning and running for high ground, our human OS decides to sit down and build elaborate sandcastles because it hasn't rained in a few weeks.
That's a very apt way to put it.
Which perfectly brings us to the final critical section of the archive, field synthesis, the concepts of citizen science and survivability. Because if the macro grid is fundamentally vulnerable to a simple summer heat wave and simultaneously facing a $2.6 trillion space weather threat with massive multi-year replacement delays, the only logical, rational conclusion for the future of technological resilience lies in decentralized, survivable systems.
Precisely. You cannot rely solely on the massive, fragile macrostructure to preserve critical data and communication. You must ensure the independent survival of the micronodes.
And this is where we synthesize the Hoth buffer theory we discussed earlier with the practical, brutal, operational needs of decentralized infrastructure in a post-event environment.
Right, because if a coronal mass ejection takes out the main grid for a year, society is going to instantly require localized edge computing nodes to coordinate emergency logistics, run localized medical AI, and maintain shortwave communication networks.
And those nodes are going to be sitting out in the extreme summer heat, completely disconnected from any active grid power. This is exactly why the solid-state phase-change material approach we unpack is the ultimate set-and-forget solution.
It is about moving from complex mechanical reliance to intrinsic material reliability, whether it is for MASK units, mobile armored system command centers, or remote edge computing nodes operated by citizen scientists trying to maintain a local mesh network. You simply cannot depend on a fragile spinning fan or a pressurized liquid cooling pump that requires external power and constant maintenance.
The Hoth buffer architecture relies on the immutable intrinsic material properties of the universe itself. Paraffin wax melts when it absorbs heat. It solidifies when it releases it.
The Peltier effect moves electrons based on absolute quantum rules. It is a law of physics. It doesn't require a software update. It doesn't need to be plugged into the TVA.
If the node loses external power, the internal silicon remains physically protected by that solid-state thermal buffer until localized power can be restored. It's like we are building lifeboats because we finally realized the Titanic isn't unsinkable.
And the archive connects this specific philosophy of localized survivability directly to the intellectual framework currently being developed at Redstone Arsenal.
Now, when most people hear the name Redstone, they immediately think of massive rockets launching payloads into space. But the archive clarifies that Redstone's true function in this context is acting as the intellectual brain for advanced systems design.
It's about resilient command architecture and the complex assembly of systems that refuse to die.
Yes, and the archive points specifically to a massive, highly indicative project currently underway at Redstone, the construction of the Military Systems Electromagnetic Test Support Facility, commonly referred to as MSETS.
This facility, scheduled for full operational completion in 2028, embodies the exact engineering philosophy we're discussing.
The MSETS facility. The documentation describes it as an enormous anechoic chamber. What exactly does that mean in the context of electromagnetic survival and everything we've talked about regarding space weather and heat?
An anechoic chamber is an environment mathematically designed to completely absorb all reflections of electromagnetic waves. It creates a simulated free field environment. It is essentially a perfect electromagnetic void.
Okay.
By placing decentralized electronic brains, these critical AI micronodes, into this perfect void, engineers can subject them to intense simulated stress without interference.
They can bombard the ruggedized cases with simulated electronic warfare, massive multi-spectrum signal jamming, or severe Carrington-level electromagnetic pulses.
They do this to guarantee that the internal systems won't blind themselves with their own internal signal reflections and that the external shielding will hold against a localized GIC surge.
They are violently testing these systems in extreme simulated voids to guarantee they survive when the macro world burns down. It's the exact same underlying philosophy as the solid-state Hoth buffer.
Engineering true resilience isn't about building a bigger, thicker vault or a heavier concrete dam. It's about building highly adaptable, survivable systems that simply don't leak, break, or structurally fail when the environment, whether that environment is a cascading summer heat wave or a 17-hour bombardment from a solar storm, hits its absolute peak intensity.
It represents a fundamental, necessary shift in engineering philosophy from durability to survivability. Durability is a massive, rigid concrete wall trying to stubbornly stop a tidal wave. It looks impressive, but eventually the universe will generate a wave big enough to shatter the wall.
Survivability, on the other hand, is the ability to endure the waves,
Yeah.
process the immense stress of the impact through intrinsic material properties, and successfully continue operating on the other side of the disaster.
I absolutely love that distinction, from rigid durability to adaptable survivability. And that profound shift brings our deep dive of the Osgood-Rupert Node archive to a close today.
It's been quite the journey.
We started by diagnosing the sheer terrifying fragility of the macro grid, unpacking how our human OS traps us in a psychological delusion, assuming our actively cooled, frozen banana stand of a society will just run forever.
Right.
We zoomed all the way down to the microscopic scale, exploring the elegant solutions of solid-state Hoth buffers, replacing fragile fans and liquid pumps with melting paraffin wax and graphene superhighways to fight the three-headed monster of thermal cycling.
And then we scaled all the way back out to the astronomical existential threat of the 1859 Carrington event.
A brutal historical reminder that the universe can reach down and rewrite the rules of our infrastructure on its own terms, whenever it sees fit.
It is a deeply humbling perspective on our current state of technological adolescence. We have built marvels, but they are incredibly sensitive marvels.
It really is. So, to you listening, the next time you are sitting in a quiet room and you hear that tiny fan spinning up on your device, or the next time you are driving down the highway and you look up at a massive, high-voltage transmission tower baking in the ambient summer sun, I want you to actively remember the incredibly delicate thermal, chemical, and cosmic balance that is keeping this modern world humming along.
It is not magic, it is physics, and it is deeply inherently vulnerable.
And as we close this deep dive, I want to leave you with one final, slightly unsettling thought to mull over, building upon the profound questions raised by the archive's analysis of our cognitive blind spots.
If our human OS makes us so blindly trust the massive power grid simply because it hasn't catastrophically failed on a continental scale in our own limited lifetimes, what other fundamental, immovable physical limits of our planet or our solar system are we currently completely ignoring while we confidently build our sprawling societies upon them, simply because the metaphorical freezer hasn't failed yet?